Good morning. Today we discuss the combinations of symmetry elements. In the previous class, we discussed about symmetry elements in a cubical system. There are 23 symmetry elements in a cubical system. They are center of symmetry, that is one point of symmetry, and 9 planes of symmetry, which includes 3 straight plane symmetries and 6 diagonal plane symmetries, and 13 axes of symmetry. In that, 3 tetrad axis, 4 triad axis, and 6 diad axis. And now we consider the combinations of symmetry elements. By this, we mean we combine operations such as rotation is combined with inversion, and rotation is combined with translation, etc. It is possible if they are compatible. So, such compatible combinations gives different symmetries. The different crystal systems exhibit different symmetries. It is found that there are 32 compatible combinations of the above 3 bond group symmetry elements called simply bond groups. Crystals belonging to different crystal systems can be classified on the basis of bond groups. The first combination, it is a rotation inversion axis. A crystal structure is said to have a rotation inversion axis if it is brought into self coincide by a rotation followed by an inversion about a lattice point through which the rotation axis passes. Here we choose the combination of rotation plus inversion. A rotation is followed by an inversion about the lattice point. When we discussing about rotation, we expressed the rotation 360 divided by n, where n is some integer. So we can use rotation of 360 degree, 180 degree, 120 degree, 90 degree, etc. Here first we consider a rotation by 360 degree with a inversion. It is rotated by 360 degree and it is inverted. If this Z system, this one, if you rotate this by 360 and invert, it will be symmetric. It will coincide with the previous. Next we consider a rotation by 180. Here a rotation by 180 and an inversion. So take it, and if you rotate it by 180, this hand in up and down go this side, okay, and then we reflect it. Then after reflection it will be the, and here we consider a rotation by 120 degree and an inversion. Here when we considering this, in the upper hemisphere there is three hands placed in 180 angular distance, and in the bottom hemisphere that is inverted. So for this hand there is no hand below it. It is the opposite is here. In the similar way, if we rotate this system 120 degree and taking the inversion, then it will coincide. Lastly, we consider a rotation by 90 degree. 90-degree rotation plus inversion. So this is the rotation inversion axis. Next is translation symmetry elements. The translation symmetry elements exhibited by crystals are glide plane and screw axis. There are two translation symmetries. First is glide plane and the second is screw axis. First, glide plane. When a mirror plane is combined with simultaneous translation operation in a crystal, one gets glide plane. So glide plane means reflection plus translation. A glide plane in a crystal is always parallel to the mirror plane. So the line G, it is the glide plane. So in the figure, you see a left leg. If it is reflected, you will observe a right leg here at this distance. Here we find a right leg, then it is translated some distance. So it will be similar to a footprint or in the process of walking. Just watch it. Reflection plus translation, reflection plus translation, reflection plus translation. So here this is known as glide plane because there must be a reflection plus a translation, and this is reflected and translated. Okay, then the next is screw axis. By screw axis means a rotation is combined with translation, rotation plus translation. We know that rotation can be carried out by different angles. Here we consider one of the screw axis. Here we take the rotation by 90° and a translation. So here it is the screw axis. Then if it is rotated 90°, if this is rotated by 90°, it will come here, and just look at the structure. Here it is a yellow large sphere, and there are two small sphere placed on it, and the left is blue and the right is red. Then if you're rotating the large sphere by a 90°, we can see the blue small sphere and the large yellow sphere. Okay, so first we rotated by 90 and translated here, and this is rotated further 90 and translated. Then it comes this. Here look at the small spheres is interchanged here in the right blue, and in the left red, and it is further rotated by 90 degree. Then here a red small sphere facing us, and the blue is not seen by us. Then this is further rotated by 90 and translated, we get the initial one. So it is a screw axis. So in the translation symmetry, there is glide plane and screw axis. In glide plane, it is reflection plus translation, and in screw axis, rotation plus translation. The next is space groups. In a crystal, the point group symmetry operation can also be combined with translation symmetry elements, provided they are compatible. Such combinations are called space groups. That is, if the point group symmetry operations is combined with translation symmetry elements, such groups are called space groups. There are 230 space groups exhibited by crystals. So the study of symmetry elements of different crystals enable us to classify crystals and their properties based on different symmetries. Next is Bravais lattice. Bravais in 1848 theoretically proved that there are precisely 14 possible ways of arrangement of points in a regular three-dimensional pattern. We pointed out this in a previous lecture. Therefore, there are 14 types of space lattice possible. These are called Bravais lattice after the name of discoverer. Since the atom in a crystal are also arranged in a regular and definite pattern as in a space lattice, therefore there can be only 14 possible types of crystals. Any other type of crystals except these 14 is just theoretically impossible. So here we discuss the 14 possible types of crystal. We know that there are 7 crystal groups. So each crystal groups is classified into different categories. It combines to form these 40 types of crystals. We know that there are 7 crystal systems such as cubic, rhombohedral, triclinic, trigonal, monoclinic, hexagonal, etc. So each of these with their different combination is discussed here. So in cubic crystal system, there is three different types are available. Here the first one is the atoms are placed only in the corner, so it is primitive, and the other two are non-primitive, and in this case the atom is at the corners and also at the body center. And it is non-primitive, and this type body center is represented as type I. Body center is represented as type I, and here it is primitive, so it is represented by the letter P. And here at the corners and also at face center, so it is the type is represented as capital F. The type is represented as capital F. Okay, so in cubic there is three types: simple cubic, body centered, and face centered. Simple cubic, body centered, or face centered. And in tetragonal, two different possibilities: body centered and simple cubic. It is simple cubic, primitive, and it is body centered. Then P and I. In orthorhombic, four different types are available. The first is primitive or simple cubic. The second, third, and fourth are non-primitive, and the second is body center or it is I, and the third is base centered or it is represented by C, and the fourth one is face centered. It is represented by F. And in monoclinic, two different possibilities. First is simple cubic and it is primitive, and the second is base centered or it is represented by C. And in the rhombohedral, only simple cubic or primitive is possible. And in triclinic also, primitive or simple cubic is possible. And in hexagonal, Also, simple cubic or primitive is possible. So in a cubical system, three different lattices possible: simple cubic, body centered, face centered, P, I, and F. And in tetragonal, two types of lattices, simple and body centered, P and I is possible. And in orthogonal, four types are available: simple, base centered, body centered, and face centered, P, C, I, F. And in monoclinic, two lattices, base centered and simple, P and C. In triclinic, only simple lattice or P. In trigonal, only simple cubic or primitive, P. And in hexagonal also only one, simple or it is primitive. So it is the details about Bravais lattice. So I stop here. In the next session, we will discuss about metallic crystal structure. Okay, thank you.